Hello everybody. In this video, I want to introduce you guys to the concept of reaction rates. But first I want to talk about rates in general and specifically the difference between instantaneous rates and average rate. So the instantaneous rate is the rate of a process at any given moment. An example of that would be like the speedometer on your car. This measures the instantaneous speed of your car. It tells you how fast you're going at that moment, not necessarily how fast you're going over the entire length of your trip. If you wanted to know the average rate of your trip, this is going to be the average of all the instantaneous rates over the whole trip. You would calculate that like this. So you would travel if you traveled 30 miles in your car in 30 minutes, your average speed would be 30 miles divided by 30 minutes, or 1 mile per minute. So that doesn't mean that you were always going 1 mile a minute. It means that in average, it all equaled out to be 1 mile per minute. For some of your trip, you could have been going slower than that, and you would have an instantaneous rate that's less than this. And for some of your trip, you could be going faster than that. And we can do conversions with rates just like we did with anything else. For instance, if we wanted this in a more familiar unit like miles per hour, we would just do the exact same thing we've always done. We would take a fact that there's 60 minutes in 1 hour, and we would arrange it so that the units cancel. So here we're going to cancel our minutes, and we'll do out our math, and we see that we were going 60 miles an hour for the duration of our trip. So to calculate the average rate of our trip, we took the change in distance that we had, divided it by the change in time that it took for the trip. And when we're doing reaction rates, we're going to do the same thing, only we're going to replace the distance with the change in concentration and divide that by the amount of time that it took to change that concentration. I also want to introduce a little bit of notation to you guys. If I put something in squared off brackets, that means that you should read that as the concentration of whatever's in the squared off bracket. So let's look at a graph of a process here. So if we have the reactants in our reaction, we talk about the concentration of the reactants, and we look at that over time, we're going to get like some kind of arbitrary curve for that. What this curve looks like is going to depend on what the reaction kinetics of that specific reaction are, and it could take on a lot of different forms. Okay. The instantaneous rate at any given moment is going to look like the tangent line of the point on that curve. So if I take a point, the tangent line is going to be the one that follows along that curve and only touches it at that one point. And it's going to have the form of a line. We have y equals mx plus b. We're not very interested in what the intercept is over here. What we're interested in is this slope. The slope of this tangent line is going to be equal to our instantaneous rate. Now, if we look here, this kind of makes sense. So we start off with a lot of reactants, a high reactant composition, and as the reaction goes on, we get fewer and fewer reactants because they're all being converted to product. On the other side here, we're going to start off with less product, and we're going to be eventually getting more and more product as the reaction continues. eventually this comes to some sort of steady state where we stop consuming reactants, and eventually the products come to some sort of steady state up here. And you can see that these two graphs are going to be kind of opposite one another, right? That as a reactant is consumed, a product is formed. We can have the instantaneous rate at any given point as the tangent line over here. Now what's going to wind up happening is that if I pick out the exact same time coordinate in either of these graphs and I figure out their instantaneous rates, the slope of those lines are going to equal each other. So the rate at which it's being consumed here is going to equal the same magnitude of the rate at which product is being formed here. Only they're going to have different signs, right? So here we have a downward slope, which would indicate that it is negative. And here we're going to have a positive slope indicating that it is positive and products are being formed. So this means that the slope of this line is going to equal the negative of this slope, right? Because if I take the negative of a negative slope, I'm going to get a positive slope. To help you with some of your homework problems, I want to show you a special example of this, where we actually have a constant rate. The reactants are always being consumed at the same rate throughout the reaction, and the products are being formed at the same rate throughout the reaction. In this special example, the tangent line is always going to be the same, and it's going to be the same as the rate because it's constant throughout, right? If I put a point here and I try to draw a tangent line, it's just going to follow along with this curve. So when the reaction rate is constant, the average rate is the same as the instantaneous rate, because if I added up all of these points along here and then divided by the number of points I had, I would still get the same instantaneous rate because they're always the same. So let's take a look at an example where we can calculate the average rate of a reaction. The neutralization of sulfuric acid with sodium hydroxide produces sodium sulfate. The concentration of sodium sulfite in the reaction mixture increases from 0.23 molar to 0.87 molar in 17 minutes. What is the average rate of the reaction? So the first thing we need to do is calculate what our change in concentration was, and that is going to be our final concentration minus our initial concentration of sodium sulfite. And we'll see that during that 17 minutes, we produce 1.64 molar concentration change. The rate is going to equal the change in concentration over the change in time that it occurred. And we can calculate that by taking our 1.64 molar and dividing it by the 17 minutes that it took for that change. And we get that that our rate is 0.096 molar per minute.